Big ideas? Short lessons.
Imagine a theater with 100 seats and no seat numbers. Your ticket says, sit in the blue seat. So you walk along the rows, checking one seat after another, hoping to recognize it. Now number every seat. Your ticket says, row A, seat 7. You don't search for that seat. The number tells you where to go. That is the promise of an array. Give every item a numbered position, keep those positions in a predictable order, and the position becomes a shortcut to the item. But the shortcut has a price. If someone asks us to add a new seat between seats 2 and 3, the rest of the row may have to move. If the row is full, we may need a larger row. Arrays are fast at some jobs because of their arrangement and expensive at other jobs for exactly the same reason. Let's build one array of names: Amma, Ben, Chen, Dina, and Essie. Each name is a value. The small number beneath each box is its index, 0, 1, 2, 3, 4. The value answers what is stored here. The index answers which position should I visit. Don't mix them up. Dina is a value. 3 is Dina's index in this array. Why does the first index start at 0 in many languages? Think of the index as a distance from the beginning. The first box is 0 boxes away from the start. The next is 1 box away. Dina is 3 boxes away. So names at index 3 means, start at the array, move 3 positions, and read the value there. The answer is Dina. An index is not the item's permanent identity. Insert a new name before Dina, and Dina's index changes. The index describes a current position inside this particular array. Now we can explain why reading by index is fast. In the classic array model, equal-sized slots sit next to one another in one continuous block of memory, like a straight row of identical mailboxes. The computer knows 3 things: where the row begins, how wide each slot is, and the index we want. To reach index 3, it calculates start address plus 3 times the slot size. It doesn't open mailbox 0, then 1, then 2. It calculates where mailbox 3 must be and goes directly there. Whether the array contains 5 items or 5 million, that address calculation has the same basic shape. That is why indexed access is called O of 1, or constant time. Constant does not mean literally instant. Memory speed, caches, and the language still matter. It means the number of array items does not make us visit more positions to reach a known index. JavaScript arrays and Python lists are higher-level containers, and their runtimes manage many details. But this numbered slot model explains the behavior they are designed to give us. An array preserves order. Amma comes before Ben, Ben before Chen, and every position has a next position until the array ends. The array's length tells us how many values are currently stored. With 5 names, the length is 5, but the final index is 4 because counting positions began at 0. That gives us a safe rule. Valid indices run from 0 up to length minus 1. Ask for index 5 in a 5-item array, and you have stepped beyond the last value. Order also makes arrays easy to traverse. Start at index 0, read the value, increase the index by 1, and repeat until you reach the length. Visiting every item takes more work as the array grows. 5 items need 5 visits. 1 million items need 1 million visits. Traversal is O of n. Notice the difference. Reaching one known position is O of 1. Walking through every position is O of n. Same array, different operation, different cost. Here is a common mistake. Fast access does not mean fast search. If I ask, what is at index 3? You already know the position. The array jumps directly there and returns Dina. But if I ask, where is Dina? And the names are not sorted, the index is unknown. We may check Amma, then Ben, then Chen, then Dina. In the worst case, we examine every item. That search is O of n. An array is ordered because positions have a sequence. That does not mean its values are sorted alphabetically or numerically. If we deliberately keep the values sorted, binary search can repeatedly discard half the remaining range and approach O of log n. But keeping the array sorted creates work when we insert new values. So ask the precise question. Do I know the index? Then access is direct. Do I know only the value? Then the arrangement of the values determines how much searching remains. Now let's add a name at the end. A dynamic array often owns more slots than it currently uses. Imagine a shelf with 8 numbered spaces but only 5 hold names. Length is 5 real values. Capacity is 8. The shelf has room for 8 values before it must grow. The 3 unused spaces are reserved room, not part of the visible array data. To append Kojo, the container writes Kojo into the next free slot, index 5, then changes the length from 5 to 6. It does not shift Amma, Ben, Chen, Dina, or Essie. It already knows the next position from the length. When spare capacity exists, appending takes constant work, usually O of 1. In JavaScript, push does this job. In Python, it is append. This is why arrays are excellent for collections that mostly grow at the end: logs, samples, frames, scores, or tasks collected in arrival order. But what happens when all 8 shelf spaces are full and we append one more item? The array cannot push the wall aside. The neighboring memory may belong to something else. So a dynamic array performs a larger move. First, it finds a new block with more capacity, often much larger than the old one. Next, it copies the existing values into the new block in the same order. Then it places the new value after them and releases the old block. That single resize touches every existing item, so that append can cost O of n. Why do we still say dynamic array append is usually O of 1? Because the container does not grow by one slot every time. It reserves a chunk of extra space. Many later appends use those empty slots cheaply before another resize is needed. Spread the occasional expensive copy across all those cheap appends, and the average cost per append stays constant. The formal phrase is a mordized O of 1. The simple picture is rare shelf move, many easy placements. Appending uses the next free position. Inserting in the middle is different. Suppose we insert Kojo at index 2 between Ben and Chen. Index 2 is already occupied, so we need to open a gap without losing anything. We begin at the end. Move SE1 position right, move Dina right, move Chen right. Now index 2 is free and Kojo can enter. Why move from the end backward? If we move Chen right first while that destination still held Dina, we could overwrite a value we still needed. Backward shifting protects the data. The closer the insertion is to the front, the more items may move. In the worst case, middle or front insertion is O of n. Deletion has the mirror cost. Remove Ben from index 1 and a hole appears. Chen shifts left, Dina shifts left, Essie shifts left, until the row is compact again. Arrays pay for their clean numbered positions by doing this rearrangement work. If your program constantly inserts and removes near the front, another structure may fit better. Now the code should look like a description of the physical actions we already understand. In JavaScript, we create names with square brackets. In Python, we do the same. Names at index 3 reads Dina by index. That is direct access. JavaScript uses names .push Kojo to append at the end. Python uses names .append Kojo. Both usually place the value into spare capacity. For middle insertion, JavaScript can use names .splice to 0 Kojo. Python uses names .insert to Kojo. Under the friendly method name, later values still have to shift. To remove index 1, JavaScript can use splice 1. Python can use pop 1. Again, the remaining values may shift left. Syntax tells the language what you want. The data structure determines the work needed to make it true. JavaScript arrays and Python lists are dynamic array-like containers. They hide capacity management, but they cannot erase the fundamental trade-offs. Arrays are a strong choice when order matters. You often read by position, you traverse many values, or the collection mostly grows at the end. That is why arrays appear in image pixels, audio samples, daily temperatures, game objects, spreadsheet rows, and almost every program you use. They are a weaker match when you constantly insert near the front, need very fast lookup by a name or key, or must always remove the highest priority item. Those jobs may point toward other structures we will meet later. When you see an array, ask 4 questions. What do the indices mean? Which operations happen most? How often will the array grow or shift? Do I know the position, or must I search for it? Remember the trade-off: numbered positions buy fast direct access. Keeping those positions neat creates movement elsewhere. In the next lesson, we'll compare arrays with linked lists and see what changes when neighbors are connected by links instead of sitting side by side. Until then, know the position, know the cost.